In this problem, we're going to look at how to find principal stresses and the max in-plane shear in the xy plane, and then look at the angles at which those occur. And we're going to do an example problem. So we're going to find the principal stresses and the max in-plane shear and the corresponding angles for a combined loading problem. So here we have a cantilever beam. So there's a compressive force F acting on the right end and a downward force V. And then we're interested in finding these stresses at point A, which is along the neutral axis of the beam. So since we've already covered how to find the stresses at an element at A, we won't repeat the exercise just to save us some time, and I'll go ahead and draw what those stresses would be, what our stress element would look like. So this is something you've had practice with now. So we know that we're going to have this compressive stress in the x direction, and we have a shear stress that is going to be acting in the negative direction. So the value of the compressive stress is F over BH, and for the shear stress, the magnitude is going to be 4/3 times V over BH. Alright, so let's go ahead and get right to what we're looking for. So first thing we're going to find are the principal stresses, and we're going to use the equation for principal stresses that are in the lecture notes. So, and we know that equation to be the two principal stresses. The in-plane principal stresses are going to be sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y divided by 2, this quantity squared, plus tau xy squared. Okay, and remember, sigma 1 corresponds, so we have a plus or minus in this equation. Sigma 1 corresponds to the plus, sigma 2 corresponds to the minus, right? Because sigma 1 is going to be greater than sigma 2. We also know, looking at our stress element, there is no sigma y. So let's put that this is sigma x. So there is no sigma y, so we know that that term is going to go to 0. And what we'll then do is substitute our values, our sigma x and tau xy in this equation, and that's going to give us what our principal stresses are symbolically. So sigma 1 and sigma 2 are negative F. And remember, the magnitude is going to be important now. So sigma x is compressive, so the magnitude is F over BH, but sigma x is actually negative because it's compressive. So we're writing negative F F over BH and then divided by 2, so that's negative F over 2BH plus or minus square root again. Watch out for our sign, negative F over 2BH squared plus, and then the sign here again, it won't make a difference here since we're going to square tau xy squared, but tau xy, notice that it's actually in the negative direction, so it's acting on the positive x face but in the negative y direction, so tau xy is actually negative. So we're going to write minus 4/3 V over BH squared. So symbolically, that would be our answer for the principal stresses. And then we want to know what is the angle of the plane where those principal stresses occur. So here we'll use the equation found in the lecture notes, tan 2 theta p. Theta p is the principal stress angle, so principal angle, and that's equal to tau xy divided by sigma x minus sigma y divided by 2. Okay, so we'll get that theta p is equal to 1/2 arctan, and then tau xy. Here's where the sign actually does matter. Tau xy is negative, so it's negative 4/3 v over bh. And then sigma y is 0, but sigma x is also negative, so that's going to be negative f over 2bh, and we divide sigma x by 2. And since it's a arctangent, that's going to give us 2 angles, right? So we're actually going to get 2 answers for the angle. One of those angles will correspond to the maximum principal stress, which is sigma 1, and one of those angles will correspond to the minimum principal stress, which is sigma 2. So I want to make sure this is really clear, so let's actually plug some numbers into this. So what we'll do, let's let F be equal to 10,000 pounds. Let's let V be equal to 5,000 pounds force. And then let's let B and H both be equal to 3 inches. Okay, so I won't do the calculations here. I'll let you practice putting that into your calculator. But if we were to plug these variables into the equations that we just looked at above, we're going to get that sigma 1 is equal to 370. Oops, that didn't come out quite right. It's equal to 370.4 psi. Sigma 2 is going to be equal to negative 1481.5 psi. Okay, so that's our maximum and minimum principal stresses. And then just, if we were to calculate theta p from the above, we're going to get our 2 angles to be 26.6 degrees and 116.6 degrees. Notice that these angles are 90 degrees off. That's always going to be the case for your maximum and minimum principal stress. They'll be separated by 90 degrees. Alright, so what we want to know though is which one of these angles corresponds to the maximum principal stress, which one corresponds to the minimum principal stress. So what you do is you'd go back to our equation for sigma x prime. So that's just the equation to get the stress transformation from the xy coordinate system to some rotated coordinate system in the x prime y prime coordinate system, and you'd plug in one of these angles for sigma x prime. So if we were to calculate sigma x prime using theta equals 26.6 degrees, and again, just because we don't have a lot of time on this video, so go back to the first video to remind yourself of that equation for sigma x prime. It's dependent on theta. Or go back to the lecture notes, see what that equation for sigma x prime is dependent on theta. What you're going to get for 26.6 degrees is that sigma x prime is equal to negative 1481.5 psi. Okay, so what that tells us is that this angle 26.6 degrees corresponds to the minimum principal stress. And if we did the same thing, you know, we know what's going to happen now for our other angle, 116.6 degrees. If we were to calculate sigma x prime at 116.6 degrees, we're going to get that sigma x prime is equal to 370.4 psi. Alright, so what that tells us, let's go back up here. That tells us that theta P1, so that's the principal angle corresponding to the max principal stress, is 116. Theta P2 so the principal angle corresponding to the min principal stress is 26.6 degrees. Okay, so the only way to know that is you've got to go back and test your angle in the stress transformation equation to figure out if that's the angle for the maximum principal stress or the minimum principal stress. And finally, just to fully illustrate, so we have a good picture in our head of what's going on, let's draw a stress element that contains, so it's a rotated stress element showing these maximum and minimum principal stresses. Okay, so we know that our element's going to be rotated for the minimum principal stress. If this is our element in the xy coordinate system, we know we're going to be rotating it. Okay, so the maximum principal stress, we know with reference to x, is rotated 116 degrees, so that's going to be on this face, and it's tensile, so that's sigma 1. And then the minimum principal stress is rotated by 26.6 degrees from the x-axis, and that one's compressive, because sigma 2 is negative in this case. Okay, so, and just to make that nice and clear, for this one we rotated by 26.6 degrees. And this one we rotated by 116.6 degrees. Okay, so that's everything we need to know about maximum and minimum principal stresses and how to get the angles of rotation that correspond to each of those. So now let's move on to calculating the maximum in-plane shear in the xy coordinate system. So let's recall the equation for max in-plane shear, and I'm going to write xy because the plane that we care about is the xy plane right now. That's equal to plus or minus square root sigma x minus sigma y over 2 squared plus tau xy squared. Alright, so if we plug in our variables that we had for the stress element, for the situation, for that cantilever beam from combined loading, Remember, sigma y was 0, sigma x was f over bh, tau xy was 4/3 v over bh. And again, since we're squaring these, the sign doesn't matter. I'm still going to get the correct sign on here. So it's f over bh divided by 2. I should say negative f over bh since sigma x is compressive. We'll square it. And then tau xy was negative 4 over 3 v over bh. Squared. It's not meant to be a... There we go. Okay, so that would be the equation for the maximum in-plane shear. And notice the plus or minus, you'll get the same magnitude. There'll just be a plus or minus in front of that max shear. We'll illustrate that in a second, just to make that clear what that means when you're trying to draw the rotated stress element. And then to calculate the angle at which the max in-plane shear stress occurs, we have tan, this equation is in the lecture notes, tan 2 theta s meaning the angle at which the maximum in-plane shear occurs, that's equal to negative sigma x minus sigma y divided by 2 all over tau xy. Okay, so if we plug in what we know for sigma x and tau xy, we know that sigma y is 0, we're going to have that theta s is equal to 1/2 arctan so it's negative sigma x minus sigma y is just equal to sigma x, which is f over bh, divided that by 2, and it's a negative. Again, pay attention to the sign there. So negative f over 2bh and over tau xy. Again, sign is important here, which is negative 4 over 3 v over bh. Okay, so this is our maximum shear angle. Alright, now let's illustrate this. Let's put numbers to this again, just to make the illustration a bit more clear. So double check this in your own calculators or program this into your computer, just to make sure you understand the math. But at this point it's just algebra, so I'm going to skip that part and just tell you if we use the same values for f being 10,000, v being 5,000, and then letting b and h both be equal to 3 inches, then when we plug all of that in, our tau max will be equal to plus or minus So yeah, tau max is going to be equal to plus or minus 925. Oops. Here you go, one more try. Point 9 psi. Okay. And the angles that we'll end up getting when we plug them into this equation for theta s we're going to get angles minus 18.4 degrees and 71.6 degrees, because that equation will give us two answers for the angle, right? So what we need to know is which of these angles corresponds to this positive and which ones corresponds to the negative. So let's go ahead and check. If we go back to the lecture notes, there's the equation for tau x prime y prime. So it's transforming the shear stress from the xy coordinate system to the x prime, a rotated coordinate system, which with coordinates x prime and y prime. So if we go plug one of these angles into that equation, we'll see what we get. So let's go ahead and take 71.6 degrees, okay? And let's plug 71.6 degrees into that equation. You're going to end up getting that when you plug in tau x prime y prime at theta equals 71.6. We're going to get that it is equal to positive 925.9. Okay. Oops. And if we were to do the same with our other angle, negative 18.4 degrees, then we're just going to get negative 925. Oops. Try that again. So at negative 18.4 degrees, that shear is negative 925.9. So that tells us that this one here, 71.6, is theta S1, and negative 18.4 is theta S2. And again, let's draw what that means on a stress element. So, and notice they're separated by 90 degrees, but let's take a stress element. If it were rotated by about negative 18.4 degrees, that's maybe a bit too much, negative 18.4 degrees with respect to the x-axis, have something that looks like this. And so if we were using the stress transformation equation for 71.6 degrees, that would be as if we were saying, for that case, that our x prime was in this direction and our y prime was in this direction. So we're rotated 71.6 degrees from the x-axis. So I'm going to draw sorry, pen's struggling a little bit. But yeah, 71.6 degrees. If we were treating that as its own transformation, we'd have coordinate axes x prime and y prime like this. And we were getting, in these coordinate axes, that the shear was positive. So we'd have this shear positive, drawn positively. It would have the magnitude of 925. If we were from the same x-axis to go rotate negative 18 from our x-axis, then that would be as if we were doing a transformation to then that would be as if we're doing a transformation from using an x-axis pointed negative 18 degrees, rotated negative 18 degrees from our x-axis, so we'd end up with x and y that's rotated like that. So then if we were to draw a shear on this one in the negative direction, right, so our x and y axes would be like this for that rotation. So it's almost like treating like two separate rotations, and our shear would look like, for negative 18 degrees we get a negative shear, so for this rotation of the x and y axes, the negative direction would be drawn like this. Okay, so that shows you what the max shear would look like on the stress element. One other thing to note, you actually will still have a normal stress. So even though when you have a principal stress, there's no shear. When you have your max in-plane shear, you still have a normal stress. I just want to make note of that. So when you draw your stress element, you still have normal stresses when you're at your max in-plane shear. And these normal stresses, when you're at your max in-plane shear, are equal to what we're going to call sigma average. Let's pull this up. And we weren't asked to compute this in this problem, but I just want to make note of it. It's getting a bit messy now, I know, but when we have our max in-plane shear, just remember there's still a normal stress that exists on that element, and that's equal to sigma average. And sigma average, it's the average of the two in-plane normal stresses. So that's sigma x plus sigma y divided by 2. Okay, so that's how we calculate our principal stresses, doing it all using equations. In the following videos, we're going to show how to do it visually, which might make a little bit more sense, and it's easier just to see everything that's going on when we do that.